Okay, so for the last class and a half, we've been talking about the Mobius inversion formula. And we did a bunch of applications in the last little while. So for the poset of divisors of an integer, we got the formula for Euler's totient function for the phase poset of a polytope. We saw that this relates nicely to Erhard theory, and for the Boolean lattice, we saw that this is precisely what's called the inclusion-exclusion formula, and we saw this application of basically if you a different way of saying this application that I told you about the drunken people and their hats is if you pick a random permutation of the numbers from 1 up to n, what is the probability that no number is in its correct position? And we saw that that's about 1 over e using Mobius inversion. Now, my goal for today is to do the application that most interests us at this point, which is to apply this to the poset, the intersection poset of an arrangement. Okay. So today, we're going to do it for P, the intersection poset of a hyperplane arrangement. Okay. So let's do an example. Let's say that we're in R2 and our arrangement looks like this. Okay. So the equations are x equals 0, y equals 0, x equals y, and x plus y equals 1 in R2. Okay. And so then maybe I'll label these hyperplanes. Let me see if I call them anything here. I didn't, so I don't know. Let's call them 1, 2, 3, and 4. Okay. And so then we saw how to draw the intersection poset. We have a lowest element that represents R2. Then we have the 4 hyperplanes. One, 2, 3, and 4, which are the lines of the arrangement, and then we look at the points of intersection, which are going to be this one, which is 1, 2, 3. So I just call it 1, 2, 3. Then this point is 1, 4. And 2, 4, and 3, 4, right? So that's the intersection poset. And then if we compute the Mobius function, and let me label the bottom element with the empty set, just to say that there's no hyperplanes in that intersection. Okay. And now the Mobius function is going to be, let's see, 1 here, minus 1, minus 1, minus 1, minus 1. And then here it's 2, 1, 1, 1. And so then the characteristic polynomial we said is obtained by making a polynomial out of the, we take these row sum, so you get 1 here, then minus 4 here, and then 5 here, and the characteristic polynomial is q squared minus 4q plus 5. Okay? And in general, the characteristic polynomial of the arrangement is given by the sum over the elements in the intersection poset. So let's call them, what did I call them here? F. So F is an element of the intersection poset. Okay. And we call them F because we said they're called flats. Okay. And then we take the Mobius number of that element and q to the dimension of that. So this is a two-dimensional intersection, so it gets a 2. One-dimensional intersections get a 1, and this is 0. So q to the dimension of f. Okay? So that's the characteristic polynomial of the arrangement. Now, by now we've seen a bunch of expressions that look like this, and by now we have seen this enough times that we can expect that if you have a summation of a Mobius number times something, then that's calling for us to invert that, and write this as a sum of things that look like this without the Mobius number. Okay, so this is almost, it looks like the aftermath of Mobius inversion. And that's what I want to make precise. Okay? And what we're going to get is very interesting and very beautiful. So I don't know, let's put a little thought bubble here. This is kind of non-rigorous thinking, but through some kind of Mobius inversion, and let me make this blue because we don't know exactly what we're going to do yet. This should be something like q to the right-hand side. So something like this should be some kind of sum of something that's kind of like this. Okay? Presumably over things bigger than or equal to f. Okay? Actually, to be consistent with the way that I'm writing it there, maybe I will use G instead of F here. And then what I want to do is put some kind of F of G here. Okay? So this is what we're going to do, and let's make this precise. Okay. Now, in all of the examples that we did over there, this was the product of counting something. Okay. And so we can interpret this as some kind of counting. We're trying to come up with a counting problem such that the answer is this. And the answer is this. Okay? So can you think of a counting problem whose answer is q to the dimension of f? See, it's a little bit strange because q is a variable, right? I mean, q is the variable of the polynomial. And so if I say it like this, the question doesn't make a lot of sense. The answer to a counting problem being x to the something. That wouldn't make sense unless we give some interpretation to what q is. Okay? And q presumably should be some kind of integer if we want a counting problem. Okay? So I don't know, let's say that q is, I don't know, some integer. Then can you think of a counting problem whose answer is q to the dimension of f if q is an integer? this counts the sequences of length, the dimension of f, with entries between 0 and q minus 1. That's true. So this is rigorous. Let's put it in black. Q to the dimension of f is the number of sequences. Let's call them x1 up to x sub the dimension of f. Such that each xi is between 0 and q minus 1. Okay? Now, we do have a dimension here, though, right? So you should be thinking that the dimension is talking about some kind of vector space. Okay? And so we're looking at n tuples, numbers between 0 and q minus 1, and then there's supposed to be some kind of dimension. Well, the next insight you might have actually is that there are vector spaces that are finite because there are fields that are finite. And we don't often do this. Normally the vector spaces that we consider are either real or complex. That's probably what you're most used to. But you surely know that there's finite fields, like the field FQ. Okay? And if you have a field, that means that you have a notion of vector space. Right? And what's a vector space? It's exactly something like this. So if Q happens to be a prime number, for example, then here you're just precisely giving me a point in a vector space of dimension of f. In other words, this is precisely the same thing as taking your f, which was a subspace, and now regarding it as if it lived in fq, not over the reals. Okay? And so that's basically what we're going to do. We start with a real arrangement, and then I'm going to do this kind of strange thing, where I'm going to just pretend that I don't live in R2, that I live in the vector space, the two-dimensional space, but now not over the reals, over the finite field FQ. Okay? So let Q be a prime. And let FQ be the finite field of Q elements. And you know how this works. Addition is mod Q, multiplication is mod Q, and then the reason you can divide is because Q is a prime, and so these things have inverses mod Q. Okay? And now let's consider the arrangement. Consider A as an arrangement over FQ. And so what I'm going to do is I'm going to take R2 and instead turn it into something like FQ2. Okay? And let me do it for a concrete Q just so that I can draw some kind of picture. So let's say, for example, that Q is equal to 5. Okay? And let me draw the plane FQ squared. Now, have you guys ever drawn a plane over a finite field? What does that look like? I mean, it doesn't really make sense to draw it the way that we usually draw planes, because how many elements are in FQ squared? Basically, you get to choose an x and a y such that x and y are between 0 and 4, right? So this can be 5 things, it can be 5 things, so there's 25 points. So this is a finite vector space. And so we probably shouldn't draw it like a continuous thing if it only has 25 things. This vector space has 25 elements. And if I asked you to draw them, how would you draw them? What's that? I would do some kind of lattice, right? So let's draw a 5 by 5 grid. And that's going to represent fq squared for us. Okay, so for example, this is the point 0, 0, and let me forget about the parentheses just so this is easier to write. So this is 1, 0, 2, 0, 3, 0, 4, 0. This is 0, 1, 0, 2, 0, 3, 0, 4, so on. So for example, this one is 4, 4. Okay. So that's my vector space. It's just a bunch of points. Okay. Now, what are the hyperplanes then? So, what's the hyperplane x equals 0? Well, you basically go here and see who has an x coordinate equal to 0. And it's going to be these 5 points, right? And you're kind of tempted to draw the line just like it looked over there, but it's really just those 5 points. Okay, so you draw it maybe like this. Those are the 5 points that form the hyperplane x equals 0. Now what about y equals 0? Well, y equals 0 is these 5 points, right? So here's y equals 0. Okay. What about x equals y? It's this kind of diagonal here, right? 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4. And what about x plus y equals 1? Well, is it that? I have to wrap around because remember that everything I'm doing mod 5, right? So 0 plus 1 is 1, 1 plus 0 is 1, but also, for example, 2 plus 4 is 1. So this point is on there. 3 plus 3 is 1, and 4 plus 2 is 1. Okay. So that's the hyperplane. It kind of wraps around. And this shows you that actually maybe a better way to think of this is like a torus. So it looks like a grid, but really it wraps around in this way. It's like a Pac-Man board. It wraps around in this way, and it wraps around in this way also. Yeah. So that's the arrangement, which instead of calling it, let's say that I called my original arrangement A. Okay. Now I'm going to call this arrangement the arrangement A sub Q. Okay. To signify that I'm taking the same equations, but I'm regarding them as existing mod Q. Okay. So now, let me state for you the beautiful theorem that we're going to get out of this. So theorem. The characteristic polynomial of Q is going to be just the number of points here that are on no hyperplane. Number of points in fq to the n that are not on any hyperplane of the arrangement A sub Q. That's why it's a function of Q. It's a very good point. The left-hand side is a function of Q, and the right-hand side is the number of points, but that depends on how big this grid is. So.
Okay, is A and Q being overloaded, or is this going to be the exact same polynomial we have? Your chi sub A of Q, those have to match up, right? They'll recover as well.
So that's what I'm claiming, which I hope you find this very surprising, because so far I've been computing this in a very different way from what I'm saying. But I'm saying that if you do this business of turning to mod Q, and if you count the points over there that are no hyperplanes, you're going to recover this exact polynomial. Okay? So I'm saying that originally we're trying to compute the characteristic polynomial of a real arrangement, and this is how we do it. This is how we've been doing it through this process of the Mobius function. But what I'm claiming is this, that if you take the same equations, and now you forget that you're living in real space, and you pretend that you're living over a finite field FQ, so you're living here, then what you're going to do is you're going to count the points in this picture that are not on any hyperplane. And what you're going to get is exactly that. It's weird. I think it's very cool. And I think we should see it before I try to prove it. I think I better show you at least in this example that this has some chance of working. Okay. So let's try to compute the number of points here on no hyperplane. So number of points on no hyperplane. How would you compute them? Well, one thing that you should keep in mind is that I do this for q equals 5. So if I count them here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then that's not a polynomial because q is equal to 5. But what that is saying is that if you plug in 5 there, I should get 10. I hope that's right. 25 minus 20 is 5 plus 5, 10. Okay, so that matches. But let's imagine this picture now over any Q. Okay, just imagine this grid is bigger, and let's count. So how do we count this? Well, what we could do is we could say, first consider all the points. Okay, all the points. So how many are there? There are Q squared of them, right? Now let's subtract hyperplane per hyperplane. So subtract. So let's subtract these points. Okay, how many points are there? Well, Q, right? And let's do it for the other ones. So there's Q here, there's Q here, and there's Q here. Is that clear what I'm doing here? So first I subtract these Q points, then I subtract these Q points, then I subtract these Q points, and then I subtract these Q points. Now, why is it that there's Q points in any of these counts? Well, you could try to make some kind of careful argument, but actually you should realize that this is a line. And it's a line over FQ. And a line of dimension Q has to have Q points. A line of dimension 1 has to have Q points. And in general, if you're over a finite field of Q elements, then a space of dimension K has Q to the K points. So this one has Q squared. These ones all have Q points. Now what happened? I overcounted, right? So I should add back what I overcounted. So for example, what did I overcount? I overcounted this point right here. I subtracted it twice, so let's add it back in. Right? This one, I should also add in. This one I should also add in. And this one I should also add in. then I should be done. Am I getting the right answer? I'm not getting the right answer. Why, Rika? So I actually over-subtracted this guy more than the other ones, because I subtracted it 1, 2, and 3 times. So that means that I need to add it back twice. So I need to add this guy twice. Okay? And now I get q squared minus 4q plus 5, which is what I need to get. Okay? But you should realize something even stronger here, because I hope that what I drew here looks like the picture that I have down there. Yeah? You see, this is exactly what these terms are. Q squared minus q minus q minus q minus q plus 1 plus 1 plus 1 plus 2. Who gets the 2? The intersection of 1, 2, and 3, because they got over-subtracted 3 times. So I need to make up for it. Okay? So what this should tell you is that this Mobius function is really smart. And what this Mobius function does is exactly keep track of the over-counting in that picture. Okay? So I hope now at least you see that this is a plausible thing, that this could possibly be true. And so now we should prove it. So let's prove it. Do you guys have any questions about it? So let me say one thing here. Just let A have integer equations.
But it doesn't have to, though, right? Your poset down here doesn't rely on the fact that it's just like an intersection. It doesn't rely on integer values in your hyperplane.
So you're pointing to a subtlety that I'll talk about in just a second. Yeah, I will answer your question before the class is over. Okay. Let me try to budget my space here on this board. So this is the kind of equation that I want, the one that I'm erasing. Q to the dimension of f equals a sum over g greater than or equal to f. So I'm about to write the same equation. So proof: Q to the dimension of f equals sum over g greater than or equal to f of something. What is that something? For example, I'm trying to say, so we're saying here, this is the number of points in F, regarded as a subspace here. So for example, this 4 is the hyperplane x plus y equals 1. That corresponds to x plus y equals 1. Okay? It has q to the dimension of f points. And now I want to distribute those points into little slots, one slot for each g bigger than or equal to f. Now what are the g bigger than or equals to f? They're the smaller flats, right? So above 4 in the poset, I have 3, 4, 2, 4, and 1, 4. In other words, on the line 4, I have the points 3, 4, 2, 4, and 1, 4. Okay? So if I ask you to write these points so there's q points here, and I'm asking you to express that q as a sum of a number associated to this flat, a number associated to this flat, a number associated to this flat, and a number associated to the whole flat. Well, surely you're going to tell me, well, the Q points, you can just distribute them by saying there's one here, one here, one here, and the rest are elsewhere. Okay? And in general, what I'm saying is that Q to the dimension of F equals the sum over G greater than or equal to F of the points that are in G and on and in no smaller flat. Okay? So I'm saying the points on this line, on this blue line that I'm considering here, equal the ones that are on the line and no smaller flat. Okay, so those are the ones that are not the points, plus the ones on this flat and the ones on this flat and the ones on this flat. Okay. Let me say it for the big flat. Okay, this is the biggest flat. There's Q squared points. I'm saying take these Q squared points and distribute them among the different flats. Okay, so I'm going to say the ones that are in the biggest flat and not in anything smaller are all these leftover points. The ones that are on this line and nothing smaller are these, but not these ones that are in a smaller flat, and so on. So what I'm doing is basically looking at each point and sending it to the smallest flat containing it. And that's going to prove this equality. Okay. Over the finite field Fq to the n. And then here, this is begging that we apply Mobius inversion, right? So that means that by Mobius inversion, I get that the number of points in. Now remember that in Mobius inversion here I have x and y, and then here I keep x and y and I reverse the two functions. So I'm going to keep f here and g here and reverse the two functions. So number of points in f and in no smaller flat equals the sum over g greater than or equal to f of mu of fg q to the dimension of g. That's what Mobius inversion tells me. Now, look at what happens if I plug in. I mean, here we almost have it, right? Because I'm trying to get. Oh, I erased it. But this is almost the Mobius. This is almost the characteristic polynomial. The only thing is that this f is getting in the way. But if this f wasn't there, this would be the characteristic polynomial. Okay. Well, if you put f equals 0. F is the bottom element of the poset. Then I get that the number of points in F and in no smaller flat equals the sum over the g is greater than or equal to F, but that's every g because F is the bottom element of the poset. And then I get mu of 0 comma g, but that's just mu of g. And then I get q to the dimension of g. And this must be the proof. So the right-hand side is the characteristic polynomial, right, by definition. And why is the left-hand side what we want? Well, F is the bottom element of the poset, but remember that the bottom element of the poset is the biggest flat. It's all of Rn. Okay, all of Fq to the n in this case. So this is Fq to the n. So we're counting the number of points in Fq to the n that are in no smaller flat. Okay, And that means that they're not on the hyperplanes or anything smaller than that. So that's exactly what we wanted. And so you see the proof is, I mean, the proof is just 3 steps. This is not a hard theorem. Yep? Exactly. Because I'm basically saying, you know, I erase it, but you can still kind of see it. So I'm saying the points in the whole picture that are not in any of the smaller flats. So that's the hyperplanes and the points in this case. So that's precisely the points that are on no hyperplane. So that's the proof. Once you have Mobius inversion, it's not even a very hard proof. Okay, so I need to make 2 comments about this. The first comment, they both have to do with what Nick was saying. So the first comment is that for this to make sense, I need integer equations. And the reason is that the fact that I have integer equations allows me to interpret them as equations in FQ to the n. If I had an equation involving a square root of 2, square root of 2 does not make sense in FQ over FQ. And so I wouldn't have a way of passing to a finite field. So that's why I need integer equations, so that it makes sense to go to FQ. That's the first thing. Okay? Now, let me show you a second issue that arises. What if my arrangement was this one, 5x equals 0, 5y equals 0, 5x equals y, and 5x plus y equals 1? No, sorry, I don't want to change the equation. Let me just multiply all of the equations by 5. Okay? Well, according to the real arrangement, nothing changed. Right? Because if 5x is 0, then x is 0. But what happens if we go to the arrangement over FQ? Over f5 squared, what do these equations look like? Well, 5 is 0 now. So they look like 0 equals 0, 0 equals 0, 0 equals 0 equals 0. Right? That's not the most exciting of arrangements. It's not even a hyperplane arrangement because there's no hyperplanes there. Okay? So we have to be a tiny bit more careful. And so what we need to do is say that Q should be a large enough prime. The point is that, okay, this means that we shouldn't have done this over F5, because over F5 we lost the arrangement. But over F7 we didn't lose the arrangement, over F11 we didn't lose the arrangement, over F13 we didn't lose the arrangement. So as long as we picked a big enough prime, then this would have worked out, no problem. Okay? But I need to pick Q to be big enough. So A needs to have integer equations, and Q needs to be a large enough prime. If you have rational equations, that's just like having integer equations. You just multiply by the denominator, and that's not an issue. So here, fractions are not really an issue. The problem is irrational numbers. I could have said let A have rational equations, and that would be fine.
So Q is small enough that it has to define a field, and the group structure breaks down the.
It could right. So really, what do I need? What does large enough mean? Well, what I need basically is that the intersection poset of the arrangement should be the same as the intersection poset of the finite arrangement. Okay. Now let me make a quick argument for why, if Q is large enough, this works. Basically, what I need to do is I need to make sure that every one of these flats that I have here gets reduced to the correct dimension here. So you see the problem that we had if we picked all these 5s and we went to F5 is that things that are one-dimensional here become two-dimensional there. Right? An equation 0 equals 0 is satisfied by everybody. So the hyperplanes here become the whole space there. So I don't want to lose dimension. Or gain, I don't want to gain dimension, rather. I could also lose dimension, actually. So what I want is to get the correct dimension. Okay? Now, how can I guarantee that that works over a large enough Q? Basically, because if you have any k-dimensional flat, then you guys learn in linear algebra how to parameterize it. So you're able to pick a basis of k vectors and say that that vector space is given by the linear combinations of those k vectors. Okay? And now what you do is you take those vectors and you regard them as being over Fq. And the question is, they were independent there, are they still independent? Okay? And if they are, then they're going to define a k-dimensional thing here. Okay? And the problem is precisely that here the vector 5, 0 is independent, but when we reduce it, it becomes 0, 0, which is dependent. Okay? So what you need is basically that things don't become dependent when you don't want them to be. And then you can guarantee that by sending Q to be really large. How can a dependence occur? Well, a dependence can occur because of some linear equation. And so as long as you make sure that the coefficients of the linear equation didn't get mapped to 0, you're fine. Okay? That's a hand-waving argument for why this works out over a large Q. Okay. So that proves this theorem, and this is a really wonderful theorem. This is one of my favorite theorems of the field, and it's called the finite. People call it the finite field method. We get the finite field method for computing characteristic polynomials. And by the way, one thing that you can think now, you have a homework due on Monday where you need to compute this for an arrangement. And so now you have another tool that you can use. And I think you'll be happy to see how nicely it works out. What I want to do now is show how this method works in practice, because it's really quite powerful. Okay. So here's a hyperplane arrangement. The n-coordinate hyperplanes. Okay. And I ask you to compute the characteristic polynomial of that. Okay. So think about it. In the old method, what you would have to do is that you would have to take these hyperplanes and find all possible intersections of them, find the Mobius function. Actually, you know what? We're going to do it. We're going to do it, and it's not so bad, because you have the hyperplanes x1 equals 0, x2 equals 0, and so on. What happens when you intersect x3 equals 0, x4 equals 0, and x7 equals 0? Well, you get a flat where x3 equals x4 equals x7 equals 0. So what does this lattice look like? Well, in the bottom, we have the empty set, no hyperplanes. Then you have 1, 2, this is for n equals 4. 3, and 4. So those are the 4 hyperplanes. Okay. Now when you intersect 1 and 2, you get a hyperplane that we call, you get a flat that we call 1, 2, and that's where x1 equals x2 equals 0. When you intersect these, you get x1 equals x3 equals 0, and so on. And every pair of these intersects in a different two-dimensional flat. Okay? To the last one, which is 3, 4. Okay? Now what happens when you intersect 3 at a time? Well, no matter which 3 you intersect, you're going to get something called xi equals xj equals xk equals 0. So for example, if you intersect 1, 2, and 3, then you get x1 equals x2 equals x3 equals 0, and that's above this, it's above this, and it's above 2, 3, which is just like this. And then you get 1, 2, 4, 1, 3, 4, and 2, 3, 4. Those are the triple intersections. What happens when you intersect the 4 hyperplanes? Well, then you're going to get x1 equals x2 equals x3 equals x4 equals 0, which is the origin. Okay. And so that's what the poset looks like. Do you recognize it? This is the Boolean poset, right? Every intersection of hyperplanes is different, and so I get one set for each intersection. So that means that this is the Boolean poset. So now you see why I wanted to compute it, because it's actually nice. So the lattice is just the Boolean poset, and that means that we know the Mobius function, right? The Mobius function has 1s here, then minus 1s here, then 1s here, then minus 1s here, and then 1s here. Okay. So then when we go to compute the characteristic polynomial, what do we get? We get 1. So here we get q to the 4. 4, 3, yeah. Now here you get 4 times q cubed. Here, how many things do you have? 1, 2, 1, 3, 2, 3, 1, 4, 2, 4, 3, 4. Because they're the pairs, right? So it's the 6 pairs. Then you have 4 triples. And you have 1 like this. What you get is just the binomial coefficients, right? The kth level has the k subsets. Okay? And so here what you get is just q to the n minus n choose 1, q to the n minus 1, plus n choose 2, q to the n minus 2, and so on. I mean, in this case, this is just the binomial expansion of q minus 1 to the 4. And in general, the characteristic polynomial is just q minus 1 to the n. Okay? So that's nice, it's computable, it's not too hard. Now how does the finite field method do it? You're supposed to compute the number of points x1 up to xn over fq to the n, which are on no hyperplane. So x1 is not 0, x2 is not 0, etc. So all the xi's are not 0. Okay? So then what are we doing here? Well, I mean, how many sequences are there of length n? Each coordinate is between 0 and q minus 1, but it's not allowed to be 0. That means that this coordinate could be anything except for 0. So there's q minus 1 possibilities. This coordinate could be anything except for 0, q minus 1 possibilities. Dot, dot, dot. This could be anything except for 0, q minus 1. Okay, so that's just q minus 1 to the n. It's very strange. You end up solving a totally different problem and getting the correct answer. Let me show you another example. The braid arrangement. Xi equals xj. for all I less than j. So all the pairs xi equals xj. What is the lattice? Actually, there it's hard. I mean, here this was not too hard, but here it really is hard. But what does the finite field method say? We're supposed to count the number of points x1 up to xn over fq to the n, such that xi is not equal to xj for any, because you can't get any hyperplane. Okay? So what are we doing here? We are just choosing n numbers and making sure they're all different from each other. How many ways are there to do that? Well, the first one could be any number between 0 and q minus 1. So there's q possibilities. The next one can be anything except for the one that you just chose. So q minus 1 possibilities. The next one could be anything except for the 2 that you just chose. Q minus 2 possibilities. Dot, 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 dot. The last one is anything except for the n minus 1 that you already chose. So you get q minus n plus 1. That's it. I mean, it's all, you almost feel like you're cheating. You almost feel like you consulted Google and got the answer there or something. That's it. This is the characteristic polynomial. And believe me that it's possible to do it with the Boolean with the intersection poset, but it's a lot harder. Here it's very easy. Now let's do something else. How many regions does this have? Well, remember that to compute the number of regions, you plug in minus 1 and take the absolute value. So you get minus 1 times minus 2 times minus 3 to minus n. So n factorial. And then the minus you ignore. And so that means that the number of regions. So this is the characteristic polynomial. And the number of regions is plugging in minus 1, which is n factorial. Of course, we knew that already, but I think it's satisfying to get such a clean proof. Now, of course, so I hope you liked it. This is cool. But so far, we're doing things that this result we knew, for example.